Okay, in the last class, I gave you one exercise. Actually, I was working out something, and then in the middle I left. I said that, you take it home as an exercise, and that I will do again, because that is a basic thing, basic result that I will be using today to present the FFT based implementation of the block RLS algorithm. So, let us come back to that result. Suppose xn 0 1 dot 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 n minus 1 n point sequence. Xk n point DFT of xn. Then suppose I take conjugate of each xk, call it x star k, and which I say yk. Again k equal to 0 1 dot 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 n minus 1. Then if I take the inverse DFT yn, which is n point I DFT of yk, then what is yn? That was the thing. So, yn, again it will be n point IDFT, means it is a sequence of length n only. So, yn, so let us work out yn, as we know, is 1 by capital N yk. This is by the formula of IDFT, e to the power j 2 pi k n by capital N. Summation is over k, n is fixed from outside. Then we replace yk by x star k. This product you can write as xk e to the power, then conjugate of this e to the power minus j 2 pi k n by capital N, put everything in a bracket, conjugate outside. Okay. So, it is like this. Xk e to the power minus j 2 pi k n star, which you can write as, okay, let me go to the next page where I am running short of space. So, next page. So, yn, I write this first. I first rewrite what I wrote there. This is what I had with a star outside. All right. Then you can write it as, I have to somehow bring IDFT kind of stuff. Okay. And now you know this is a complex number xk into e to the power minus j 2 pi k n by capital N, call it z1 into z2, which is the complex number, call it z. So, product is z. So, z star, if I give you a set of complex numbers and their summation, so it's like this z1 star, one complex number with a star, plus z2 star. There are capital N terms, I am just taking 2. This is same as I have discussed this already, z1 plus z2 star in the previous class only. So, I can even put it like this, xk e to the power minus, that is first sum and then star. All right. Now, this inner summation I want to write in the IDFT form. So, there I should not have minus sign. Minus sign comes in the DFT. So, therefore, what I will do is simply do this xk, I bring this factor e to the power j 2 pi k capital N by n. So, you see n and n cancels and k is an integer e to the power j 2 pi k, that is always 1. So, this is nothing but 1, and this other stuff. which is basically e to the power j 2 pi capital N minus n, k is common, by n star. All right. So, first put k n equal to 0, take n equal to 0's case, y 0. So, if you put n equal to 0, it is e to the power j 2 pi n by n, n into k by n, n cancels, e to the power j 2 pi k is 1, okay, and small n is 0. So, this entire factor is 1, or sorry, this is x k missing here, this is x k. So, it is summation of this, I mean x k into 1 by n star, which is basically, this, that 1 by n x k e to the power j 2 pi k n by n, if you sum over k, okay, you get x n. This is the inverse DFT formula, ordinary inverse DFT formula. So, at n equal to 0, if you put 0 here, e to the power 0 is 1. So, it is just summation of x k's divided by n. That is what we have here. This is turning out to be 1 if small n is 0, because e to the power j 2 pi capital N into k by capital N, it is 1. So, I get nothing but x of 0. So, this is x of 0 with a star outside. So, x star 0 for n equal to 0, and for n 1 to up to the last point n minus 1, it is nothing but y n is equal to capital N minus small n. If you call it an index, small n is, when small n is 1, it is capital N minus 1. When small n is 2, capital N minus 2, dot dot dot. When small n is capital N minus 1, it is 1. So, you get various values of x n, because this is nothing but IDFT at capital N minus n. Instead of small n, it is capital N minus n. So, it is, that means, and there is a star of course, that means if originally you had thing like this, x 0, x 1, dot dot dot, x n minus 1. Now, y n will be, y 0 is nothing but x 0 with a star. So, y 0 will be x star 0, this is y 0. But then at point 1, when small n is 1, this small n 0, 1, dot 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 n minus 1. So, when small n is 1, it is x star n minus 1. So, this guy will come, okay, x star n minus 1. Then when small n is 2, x star n minus 2, this guy will come, and dot dot dot, when small n is last point capital N minus 1, it is x star 1. That means, if you take this part, first part x 0, it just remains there only with a star, but this part gets flipped, x n minus 1 comes here with a star, x 1 goes to right hand side, it is just flipped. Okay. Here you started from x 1, then x 2 up to x n minus 1, here it is n minus 1, n minus 2, dot dot dot, x 2, x 1 with a star. So, it gets flipped. So, leave the first guy as it is with a star, and the remaining part you flip, of course, with a star. This is what y n is. Okay, we will be using this, remember this. Now, we come to our block LMS algorithm. In the block LMS algorithm, you know that we divide the data into non-overlapping blocks. For every block, the filter weight is fixed, it is not updated. We update it only when we move from one block to the next block. Then we use the block LMS formula, all right. And within the particular block, we use the same filter, carry out convolution and find out the output error and all that, okay. But remember, we told you how to carry out this block partitioning and then convolution, that is by overlap and save method, okay. That is, suppose Okay. Suppose your original block is this, one particular block of length L, all right, length L. But in the previous block is here, actually they are in the same line, I am showing it separately. What we do, we make an extended block of this. So, if it is ith block, if it is I minus 1th, ith block, we start with an extra part here, length n minus 1, n filter length. All these were discussed earlier, n is less than L. So, this is my extended block. Here I take this block separately, convolve the data here with the particular filter coefficient vector for the ith block, which is fixed for the this ith block or ith extended block. But then I discard the output here and take output from here, find out the output error, that is desired response minus filter output from this point onwards. Keep them for the update, for updating the weight vector from ith block to I plus 1th block. Like I plus 1th block will be here. Originally here, but we extend it again by n minus 1. Okay, this is I plus 1th block. So, we take each block separate, each extended block separately, carry out convolution with the corresponding filter impulse response vector or filter coefficient vector, which is fixed for that particular block, doesn't change, doesn't update. Carry out the convolution by overlap and shape. That is, we discard the convolution output at these points, we take convolution output here, and this can be done efficiently using FFT. We told that if you now take out, this filter, this data block, and take the filter block, suppose this is the filter block, for that it's only up to here, okay, 0 to n minus 1. So, total length is n here, and we fill up this with zeros. Then first n minus 1 output, if we carry out circular convolution, that is, if you take the FFT of this block, FFT of the filter coefficient block, for ith block. So, FFT here or DFT here you multiply, take IDFT, which is a circular convolution between this block of data and this extended filter block, extended with these zeros. Then the circular convolution, first n minus 1 results are incorrect, which is fine with me, because otherwise I was going to discard them. From this point onwards till this point, results are correct. Okay. So, what I do, I take a particular block for explanation. So, let us take this block to be like this. Okay, so this is 0, 1, maybe up to n minus 1, sorry, n minus, let me do it in a better way. So, this is, and we expand. So, this goes from, this is length n minus 1. So, that means if I start from 0, it should go up to n minus 2th point. So, 0 to n minus 2, length is n minus 1. Okay, n minus 1, and then this is n minus 1 on the time scale, this is a time scale, n minus 1 to what? This length is capital L, this length is n minus 1. So, total length is L plus n minus 1, okay, L plus n minus 1. So, this will be what? 0 to L plus n minus 2. Then only total length is total length this much is L, isn't it? And this much is n minus 1. Total length is L plus n minus 1. So, if you start at 0 and go to the right, extreme right point will be L plus n minus 2. Then only total length is L plus n minus 1, because you are counting from 0. So, this is the block we are considering. Okay. So, what we do? We start with xn. We put them in a buffer. This input data in a buffer. Length L plus n minus 1. So, these parallel lines come because all this data, this data, I mean this for the block of length L, which is the block of our actually interest, and this extra part which we added for doing the overlap shape. So, total length is L plus n minus 1. So, these fellows parallelly come out. Okay, I take FFT over it. Total length L plus n minus 1, let me give it a name L1. So, L1 point DFT. Instead of showing so many lines, I just do like this. And suppose I also have, because I am currently dealing with a particular block, extended block. So, I know what the filter coefficient vector is for this, and that will not be changed as long as I am in this block. That will change only when I move from this block to the next block by the block elements update formula. So, I am having this 0 to n minus 1. Okay, here is my filter coefficient vector W, and here we paired zeros. You remember that is what we discussed for overlap shape method. That is, if I carry out circular convolution between this, that is filter coefficients as it is 0 to n minus 1, not n minus 2, n minus 1, and remaining points L minus 1 points actually now, they are zeros, and then we carry out circular convolution between these two blocks, that is DFT here and DFT here multiply inverse DFT, which in time domain is circular convolution. Then first n minus 2 results are incorrect, from here onwards results are correct, and that is what I want, because my point of interest from here to here. All right. So, suppose this is my W, and W, if I take FFT with these zeros, it gives me WK. Then, so I multiply DFT into DFT. So, here WK, somehow it is available, suppose, okay, available. Then I take this out, DFT into DFT, then inverse DFT. So, I take L1 point I DFT, which is actually by the FFT algorithm. So, then I get the circular convolution YN. Okay. If you take this output, they are coming parallelly. So, if you put them side by side in a block form, as if it is a sequence, then from that YN, you must discard the first n minus 1 points. That is the overlap shape method. That is, we discard the first n minus 1 output, right. So, in fact, here only we can say if you discard the first n minus 1 points and total is L plus n minus 1, That means I take the last L points. They are equivalent. If you discover total length is L plus n minus 1, you are discarding the first n minus 1 points, okay, output, which means from the circular convolution you are taking the last L points. So, from here to here, all right, from here these points, they give me the correct convolution, all right. Then, so suppose this is now serial, they are coming parallelly, so I put them like this block, one after another serially, and then I subtract from dn plus minus, so I get en n from this point onwards, n minus 1 dot 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 up to L plus n minus 2. All right. Okay. Then I multiply this by mu. These are very standard routine steps. Okay. All right. Now I do this, and then I will explain why I am doing this. I form a block. In this block, I add n minus 1 zeros at the front. At the front, okay, and then I take so it was L length L and n minus 1 zeros, second length L1, okay, because I have added n minus 1 zeros in the front. So, then I take, and it is in time domain. So, L1 point, why I am doing this, I will explain in through diagram FFT, all right. And this I come here, and here I was getting xk, right, after DFT xk. So, this I conjugate. So, basically I get x star k. Here again let me write this because FFT output is parallel, and I multiply. And then take L point, rather L1 point IDFT. So, I go back to time domain. To explain that weight update part now, okay, I will relate whatever I was doing to the weight update part of the block LMS algorithm. Earlier I took care of the convolution, there is a filtering part by that overlap set method and all that. Now, as we have done in the previous page, this is what I have. Zero to n minus 2. This is coming from the previous block, overlap and shape part. I will discard the output from here, and then from n minus 1 to L plus n minus 2. Okay. This we have already done. This is my block. Weight update part. Okay, weight update part means previous weight or the current weight for this block, current weight for this block plus that extra term update. That weight update term we have seen in the block LMS algorithm. we will first take the error at this point n minus n 1, e n minus 1 into the data vector here. Data vector here is starting from n minus 1, x n minus 1 and another n minus 2 elements, these are here. Okay, x n minus 2 dot 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 up to x 0. Then plus, then I go to this point n minus 2 n. So, E n, again data vector there. So, earlier it was n minus 1, now it is x n. Earlier it was n minus 2, it is now one step forward, dot dot dot, it is x 1 plus dot dot dot. Lastly, I take at this point E L plus n minus 2. At this point the error. How is the error calculated? I have done the filtering at this point using the weight vector fixed for this block, okay, and then subtracted the output from the desired response at this point of time. That is my error E L plus n minus 2 at that point. That into the data vector here we start at this index x L plus n minus 2, next is 1 less, so n plus n minus 3 dot 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 dot. If you count, total should be capital N because there is a filter length. So, this one should be x L minus 1. This is the computation also I want to do by this DFT using circular convolution and all. That is what I was doing there. Okay, suppose I have got this data xn. This is my xn. This is my xn. So, suppose it is x 0, x 1 dot 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 dot. I go up to L plus n minus 2, all right. In fact, you can say x n minus 1, x n up to x L plus n minus 2. This is that block. So, this is the data. Okay. So, if I take x star k, in time domain it corresponds to maybe say x prime k, x prime n. So, I know what is x prime n, that is this remains as it is, just get conjugated. Now, for simplicity I am considering real data, okay, for your sake, which means conjugation has no meaning. That is why I will not conjugate, which means x 0 will remain x 0, no need to conjugate because I am considering that all the data to be, all x 0, x 1, all data to be real and for our purpose. So, conjugation has no meaning. So, x 0 will remain as x 0, but the remaining part, this part will get flipped. So, next will come x, this fellow L plus n minus 2, then will come x L plus n, before that minus 3, okay, dot 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 dot. So, this will get flipped, this x of n will come before x of n minus 1 because it is flipped. So, somewhere here we will get this x of n, there is your x n minus 1 and dot 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 finally x 1, at this point x 1. Okay, this is what will happen because I have taken the conjugate of that DFT and then inverse DFT. Okay, that is in time domain it corresponds to, that is a conjugated DFT in time domain corresponds to this. And you remember I am multiplying after conjugation, I am multiplying this with what? In time domain I formed a sequence where the error started at n minus 1, then n minus 2 up to here, but I padded with n minus 1 zeros. there is n minus 1 zeros in the beginning. So, 0 0 0 0 0 and then E capital N minus 1 capital N minus N capital N plus 1 up to this. The larger sequence, and then I have taken FFT of that. FFT into this FFT and inverse DFT means circular convolution in time domain between the corresponding time sequence here and here. Here it is that flipped version we have already discussed, alright, flipped version we have already discussed, and then this thing, I mean, and here we already know what the time sequence is. Okay. So, now we have to do a circular convolution of them to understand what is coming here. Okay. So, we know how to do this circular convolution. First, we plot that error part. Initially, I have got 0, 0, 0, 0 up to n minus 2, up to n minus 2, 0. And then I have got E n minus 1, this is n minus 1 is point, E n dot dot dot, this point and this point is the same, E L plus n minus 2 and zeros. To circularly convolve, what will I do? I will make a periodic version of this and flip it, and then keep moving to the right by one shift, and then within this period 0 to L plus n minus 2, see the I mean samples here and term by term multiplication addition. This we have done, no need to explain again. So, if you do that, what will happen is this, just if you make it periodic and flip it, this 0 will go to this side, these zeros 0 0 0 0 up to here, that is minus, it was plus n minus 2, so it will be minus n minus 2, and then all these fellows E n minus 1, E n, these fellows will just go to this side, dot 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 E L plus n minus 2, and this thing will repeat. So, again here the same fellow will come here, E then next will be E L, before this whatever was L plus n minus 3, dot 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 dot, and after some time remaining zeros, because you see this is one block, right, this is one block, I started period from here. So, whatever I have up to this, that entire thing will repeat here, alright. So, that is why from here to here, here to somewhere here, I am getting, and then these zeros, so zeros will come here, alright. Now, if you multiply samples from here and here, sorry, not here, because I have taken the conjugate of DFT and then inverse DFT. So, it is this sequence, this sequence. Now, you see this 0 multiplies this guy, nothing. So, I start with E L plus n minus 2 into x L plus n minus 2, that is this term, E L plus n minus 2 into this, plus E L plus n minus 3 into next term, which is not shown here, and dot 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 dot. Then I have got E, see this E n will multiply x n, and E n minus 1 will multiply this. This is very clear from here. This is nth here. So, this into this into this, dot dot dot, finally it will be up to E n minus 1, E n minus 1 will multiply here, actually since it is x n, I should plot it here. below xn is En, and below xn minus 1 is En minus 1. Then the zeros. You can see En into xn, En minus 1 into x minus. So, you get the first row. Then you shift it to the right. So, 1 0 comes up, 1 0 comes in. So, El minus L plus n minus 2 now multiplies next sample, this sample. That means I am now here, El plus n minus 2 into the second guy now. Okay. And similarly, this into second guy, this into second guy. So, this second row is evaluated. And this you go on doing how many shifts? Because I need 1, 2, 3 up to n, because filter length is n. So, I do it for 0 shift, 1 shift up to n minus 1 shift. That is first n shifts, get those results. All remaining results are not required. So, there I will put them, take them zeros, all zeros. So, I will take the circular convolution, I will take 0 shift output, first shift output, second shift output up to n minus 1, capital N minus 1. So, total is capital N, because I have got 0th row, first row, second row up to n minus 1th row. Total length is capital N, because this is coming with respect to weight. Okay. W, if it is called Wi, ith block plus this. So, this is length n. So, this has to be length n. So, I will take update of length n. So, 0 shift, 1 update, 1 term, first shift, another term, and like that. Alright. But circular convolution will give me a longer result. So, remaining subsequent terms I will take to be 0. Okay. That means what I will do here is this I got a circular convolution. So, this is my time domain sequence. So, I take it as it is, just make the last terms. How many terms? Because convolution, this is a L plus n minus 1, this is a total length, out of which n is gone here. So, remaining is L minus 1. So, make the last L minus 1 points equal to 0. So, update term will be such that if it will be a vector like this, of which the top part will have that update term as we calculated, that is a as we calculated the update term, and lower part, this part will be here 0. So, that zeros plus zeros they remain 0, because even when W is updated for the next block, I want this part to remain zeros. This is what is required, as you have said, for the overlap and same business, right. So, this part should not get disturbed into some non-zero elements, right. That is why this L minus 1 zeros are here. If it is the weight update term, first n minus 1, first n points, they give me weight update 0 to n minus 1. So, they get added with this. So, it gets updated, but last L minus 1 points, I am forcing them to be 0. So, that 0 plus 0 is 0. So, zeros are maintained. That is what is obtained. So, here what I get is in the time domain, I get in the time domain new weight, but I am working here in frequency domain. So, now new, there is updated weight, where I have got the data here, where weight values here, and as before zeros here. So, this extended updated weight block, on that again I apply FFT, because I have to go to frequency domain WK. So, I apply FFT. All right, all FFTs are, I am not writing everywhere, all FFTs are L1 points. L1 point. Okay, even if it is not mentioned here, there is only one point FFT or IFFT, that is L1 point. So, this is my new one, new weight, new update. All right, because I am going into this frequency domain, so new update. So, existing weight with zeros plus update block with zeros. In frequency domain, DFT of this plus DFT of this will be new DFT. This is DFT of the updated weight. I am repeating again, this is my block which means the first part is the current weight vector and then extra zeros here. That added with update term which we calculated here. Update term also has L minus 1 zeros at this lower part and upper part has the update values. When you add them in time domain, you get the new weight update for use in the next block. We are in the frequency domain, so if you take DFT of this updated weight, it is nothing but DFT of this previous weight plus DFT of the update term. So, DFT of the update term is coming here, I am taking this 50 and this is the DFT of the current weight. So, I have to add them to get the DFT of the weight of the next block. So, here I add so this gives me, if you call it Wk, this I call Wk plus 1 and then symbolically I say delay by a block delay. That is, when I move to the next block, then this fellow comes here, okay. Again it starts doing the filtering operation and all that, alright. This is the FFT based implementation of the block LMS algorithm. I hope you understood. You please go through DSP book by Oppenheim, Schafer or Proikis and all to read little bit more about circular convolution and think about what I said so far. It should not be difficult, okay.